4x minus 2 is bigger than or equal to negative 2. So this was the compound inequality here. So the strategy is you want to treat these as being separate for a while and then like glue the solutions together at the end, keeping in mind what kind of conjunction here you have. So here we have an or. So that means like a union of the two sets versus an and, which would be like an intersection of the two sets. Okay, great. So this was like I think the 6th one. So you guys might have different numbers or whatever, but the strategy will be exactly the same. Okay, so we want to get all the x's on one side of the inequality and all the numbers on the other side of the inequality. So here we can like add 2x to both sides and then also add 3 to both sides. So let's see what that gives us. So this 3 and this 3 will cancel, and this 2x and this 2x will cancel. We'll have x plus 2x is 3x, less than or equal to 24 plus 3 is 27. Now we get x is less than or equal to 9, just dividing by 3. So there we've determined the solution set for the left-hand inequality. Now, if we want to, we can go ahead and write that in interval notation. And so let's maybe do that, although that's not really required at this moment, just for practice. So it's going to be all real numbers less than or equal to 9. So that'll be minus infinity up to 9, but we include 9. So that's what we mean by this is like an inequality version of the interval given by that. Okay, great. Now we're going to do the same kind of thing over here. This one is like arguably simpler. We just have to add 2 to both sides. We get 4x is bigger than or equal to 0, which makes x bigger than or equal to 0 just by dividing by 4. Now we can write that as an interval as well if we want to. And so notice that that is going to be everything bigger than or equal to 0, which means we start at 0 and we end, well, we never end, so we write an infinity. So now you can put these together as a union. So, and that would be maybe a first solution before some sort of simplification. You could do minus infinity to 9, hard bracket, union, 0 to infinity. But the thing is that we can simplify this, and you should always try to simplify this if you see a union of two intervals by maybe like drawing a picture on the number line of what these two intervals look like and how they interact and stuff to see if you can mash them together into one interval. This is like sort of the stuff that we did in the first couple of days, but we're coming back to it over and over again so that we'll still have more practice. So that's what we'll do. Let's go ahead and make a number line. So notice 0 and 9 are important points on the number line, like that. And then maybe let's graph this one in purple. So that's going to be everything minus infinity to 9, including 9. So here I'll put a closed circle there. And then we have shading all the way to the left. Then let's maybe put this one in green. So that's going to be everything bigger than or equal to 0. So that means we include 0, we'll put a closed circle at 0, and then shade everything to the right. And now we're looking for all the numbers that are in the purple set or the green set. So one or the other. And notice the purple set or the green set encompasses the whole number line. Right? So the whole number line is given by either the purple or the green. Notice there is some overlap, but the important thing is that when you take either or, you get the whole set here. So we could finish this off by saying one of two things. If you want to put it in an interval notation, it's minus infinity to infinity. If you want to put it in words, it's all real numbers. There's also like this fancy symbol that you can use or whatever too, this like R. Okay, so maybe let's like tweak this problem just a little bit, for an example of what can change if instead of an or here, we have an and. So if we had an and there instead of an or, then everything would have been the same, except down here we would have had an intersection instead of a union, which means we would have looked for all of the numbers that are in the set minus infinity to 9 and 0 to infinity. So these numbers have to be smaller than 9 and bigger than 0. But that means they have to be between 0 and 9. So those are the only numbers that are in both of those sets at the same time. Okay, so that means the solution for this like supplemented equation would be the closed interval 0 to 9. Yeah. So I know this is like, this can be like a little unsettling sometimes whenever you get an answer and it turns out that any number works. Like here, we're saying just all the numbers work. All the numbers are solutions, but that happens sometimes. And that's okay to happen sometimes. And sometimes it'll happen that none of the numbers will work too. And that also happens sometimes, and that's also okay. Okay, so does this one seem okay? And are there others from the homework that we'd like to see? Five, four, three, two, one. Okay, so let's maybe move on. I want to do actually a couple of more problems like this, a couple of more compound inequalities, and then we'll spend like 5-10 minutes. I put just a few, not as many as the other days, but just a few compound inequalities for you to try in the warm-up. We'll maybe spend, like I said, 5 minutes, 10 minutes doing those. And then we'll come back and look at equations and inequalities involving absolute values. So that's kind of our outline for today. So review maybe 1 or 2 more like this. Then try a couple like this. And then finally, absolute values involved in equations and inequalities. And I'm still like trying to figure out my camera issue. So we're on the webcam again, but you know, I like sound treated this room, so hopefully that's okay because we're not on the microphones either. But hopefully that'll be worked out by the weekend. I can't quite figure out what is wrong with it. Okay, so let's go ahead and do maybe maybe one example, and then we'll try some, like, I'll have you guys try some. Okay, so let's say this. So let's say we have 2x plus 1 is less than or equal to 3x minus 1, which is less than or equal to x. So this is a compound inequality. And generally, there are 2 ways to do this. If you can manipulate it as is until you only have x's in the center part, then that's the best case. But we can't do that here because we've got x's in all of the parts and they all have different coefficients. So it would be hard to manipulate this until we have only x in the center. So what we will do is split this compound inequality into 2 statements with an and between them. And essentially what we're doing here is like using this fact about compound inequalities, that if you have capital A is less than capital B is less than capital C, then that can be split into 2 inequalities with an and between them. A is less than B and B is less than C. And I might as well point out that we could have less than or equal to there as well. Like, doesn't matter. So that's what we're going to want to do. Take this guy and split it into two inequalities that are bound together with an and. So I'll split it together into this purple one that I'm underlining and then this green one that I'm overlining. So let's see what happens to the purple one. So the purple one is going to become 2x plus 1 less than or equal to 3x minus 1. And then we have an and statement between them. And then the green one is going to become 3x minus 1 less than or equal to x. So there we've split this compound inequality into two inequalities joined with an and statement. Now we solve each of those separately and then essentially take the intersection of the two solution sets and maybe graphically interpret it so we can reduce it down to something as simple as possible. Okay, so let's simplify maybe this side. So maybe I'll like subtract 3x from both sides. And then I'll also subtract 1 from both sides. So let's see what that gives us. So this 1 and 1 will cancel. And then this 3x and 3x will cancel. So we're going to be left with negative x is less than or equal to negative 2. But now we don't really want negative x. We want a positive x. So what we can do is take this entire inequality and multiply by negative 1 to change the sign, or divide by negative 1. It's like the same thing. So if we do that, negative 1 times x, negative x is going to be positive x. Negative 1 times negative 2 is going to be positive 2. And then let's recall that if we multiply by a negative 1, we change the order of the inequality. So now we've worked on this left branch, so which involved this like purple underlined inequality, and we got to this point down here where x is bigger than or equal to 2. So maybe I'll box that in purple. And then maybe also it's nice to point out that this is going to be the interval 2 to infinity. Great. Now let's do the same kind of thing on the right-hand side. So maybe we want to subtract x from both sides and then add 1 to both sides. So let's see, these x's will cancel, and then these 1's will cancel, and we're left with 4x is less than or equal to 4x is less than or equal to 1. Now we can divide both sides by 4. If we divide both sides by 4, we're left with x is less than or equal to a quarter. Now let's go ahead.
Excuse me, Professor.
Yeah. Oh, sorry, that should be 2, huh?
Did you mean to? Yes, yeah.
Yeah. That was, you know, I added instead of subtracted. So we've got 2x is less than or equal to 1, which means x is less than or equal to half by dividing by 2. Now I'll box that in green to show that it comes from that side of the inequality. Now if we just look at these two statements, we can see that they're conflicting, right? And we'll see that in the graph as well. So x has to be simultaneously bigger than or equal to 2 and less than or equal to a half. So we've got to find an x that satisfies both of those at the same time, bigger than or equal to 2 and less than or equal to a half, but there's no solution there. And we can see that by making like a little graph. Notice that we can make this as an interval minus infinity to half. Now if we make a number line here, so maybe I'll use the purple and the green like I have been. So the purple is going to be like this bit right here. So we've got that. So everything 2 and bigger. And then the green is going to be everything 1/2 and smaller. But notice there's no overlap in those, right? Because of the and statement, we want to see things that are in both, but there's no overlap. So that means there is no solution to this. So this is actually a really good companion problem to the homework problem that we started with, right? Because the homework problem we started with had all real numbers as a solution, but now this one has no real numbers as a solution. There's no solution at all. You know, and that's just the situation. So this is never true. This is always false. Yeah, because again, we wanted to know where they both overlapped. Yeah. Totally different than the or statement between them. In the or statement between them, we would have had a union of these two intervals, and that would have been okay. But we couldn't have started with this compound inequality. A compound inequality like this is always going to turn into an and 7. So we've got this like or statement. And actually, as we'll see later today, these may seem like they're kind of unnatural and we're just kind of maybe not overcomplicating, but we're just like complicating a process that would never actually occur. But when we have absolute value inequalities, we'll see that these or and statements actually pop out really naturally. Okay, so anyway, we want to treat these fairly separately and then look at the solution sets for each one at the end and then glue them together. So that's what we're going to do. So we'll work each one separately. So I'll just put a line down the middle to notice that right now we're working separately. So I'll go ahead and subtract 1 from both sides here. That's going to give me 2x must be less than or equal to -6, which means x has to be less than or equal to -3 by dividing by 2. So we've got this. And then if we want, we can write this as an interval. Notice that's going to be the interval -infinity up to -3. We include -3 because we've got a less than or an equal to. Okay, so now moving on to the other one, we're going to do the same kind of stuff. So we'll subtract 1 from both sides. That's going to give us 2x is bigger than 6. And then that gives us x is bigger than 3. So this landed at the inequality x is bigger than 3. And so now we can make that into an interval by saying it's 3 to infinity, and then we put a parentheses on the 3 because we do not include it because this is a strict inequality. Now, we want to see if we can simplify that a little bit. So we probably graph it. We go down here. So -3 and 3 are important points related to this problem. So this thing right here says that we want to shade in -3 and everything to the left. This thing says that we want to shade in 3. No, sorry, don't shade in 3. Have an open circle 3 and then everything to the right. And then we go back up to our original statement and notice that it is an or statement. And since it's an or statement, we're allowed to take x values from this green shaded bit or this blue shaded bit. It's not an and, it's or, so that means either one of these is okay. So that being said, now our solution can be like written all at once as the two intervals with a union between them, so 3 to infinity. And that's how you finish it off. So you've got this one or this one. So you can always think about this union as being an or statement that occurred at the very beginning. And I know like sometimes it's not satisfying because these don't simplify, and that's the case here. This doesn't simplify any further, but that's just the situation. Like sometimes you'll be able to simplify it, and sometimes you won't be able to simplify it. Now let's like maybe tweak this a little bit just for practice. Let's say this were an and instead of an or. Then we would want to go down here and say, well, which parts of the graph are shaded both blue and green? But notice there's nothing shaded blue and green, right? This bit's shaded green, this bit's shaded blue, but nothing has blue and green shading. So that tells you that if we had started with an and between these two, we would have had no solution. So what we want to do is look for all points on the number line that are shaded both green and whatever this peach color is. So notice that in this case, it's going to be everything in this direction, right?
Yeah.
And that's because one of these conditions is okay, so wait, maybe let's step back. That's because both of these conditions are going in the same direction, but one is stricter, right?
Mm-hmm.
They're both less than type conditions, but one of them is a stricter less than type condition. Notice that if you are smaller than 1, you're already smaller than or equal to 7, right?
Yeah.
Because 1 is less than 7. So anyway, putting this all together, that gives us a solution in the end of just all points negative infinity to 1. So in fact, because this thing that I boxed in blue is more restrictive than this thing that's underlined in green, that means that we can almost like just forget about this thing that's underlined in green and only keep the one that's boxed in blue. Okay, so I came around to some of the rooms and everyone seemed to be like doing okay on these. So let's just go ahead and move on to absolute value equations and inequalities. And this actually has a really great benefit in that the inequalities will often like turn back into these compound inequalities that we've just been working with. So the absolute value inequalities give us another opportunity to practice those compound inequalities, which is nice. It just kind of adds a step before looking at the compound inequality. Okay, great. So maybe like the first thing that I want to recall, this is recall from maybe your past, not from anything that we've done, and that is the absolute value of x. So we can think about this a couple of different ways. Maybe the way that I want to write it is as this piecewise function. So this is going to be x if x is bigger than or equal to 0, and negative x if x is less than 0. So in words, this gives you the distance between x and 0, right? So like, for example, if you take the absolute value of 19, well, you look at 19 and you say, oh, 19 is positive, so I just like spit back out 19. So I get 19. But then if you look at maybe minus 2, so you look here and you say, well, minus 2 is negative, so I have to output the opposite of this, negative 2, but that's going to be positive 2. So like I said, this up here is maybe the precise way to think about this, but this right here is maybe the intuitive way to think of it, just the distance from 0. So, notice if you like draw a number line right here, we put 0 in the middle, 19 will be over here, maybe minus 2 will be over here. If we're like measuring distance, well, the distance from 0 to 19 is 19, but then this distance from 0 to minus 2 is 2. It's just a distance like leftwards instead of rightwards, but that's okay. So, this is 6 minus 5t is bigger than 4t over 3, which is bigger than or equal to t minus 2. Okay, so this is a compound inequality. There's no real hope of getting only t in the center because we have t's all over the place and they have different coefficients. So you want to think about this as this inequality that I'm underlining in purple and this inequality that I'm overlining in red. So that's going to split this thing into 2 inequalities with an and between them. And so the purple inequality will be given by 6 minus 5t is bigger than 4t over 3. And then the red inequality will be given by a 4t over 3 is bigger than or equal to t minus 2. And now we like play around with those like somewhat separately, and then put it all back together at the end. So here I'll like put a line down here to say that we're going to work separately for a while, and then put it all back together at the end. So let's see. Maybe for this one, what I would like to do is multiply by 3 to get rid of the denominator. So if I do that, so I take this thing, multiply by 3. So that's going to kill the denominator. And